So far, in this discussion about radiative transfer, we have discussed solutions with prescribed source functions. But this is not really what we want. We have two interacting systems, the radiation field and the plasma. So on the little sketch at the bottom there shows us that we have two kinds of particles in our plasma. We've got ions and electrons, charges, and we've got photons skipping around, some of which are escaping. So the fact that some of them are escaping, like the ones indicated going towards the eyeball on the right, means that there's no balance between the detailed balance. The photons are going away forever. And so that process is reducing the number of radiative excitations needed to keep it in local thermodynamic equilibrium. Okay. So imagine we have a hydrogen plasma that just has two levels. This is a fake idea. There are obviously infinite number of levels for an isolated hydrogen atom. But just for this consideration, let's consider we've got two levels in the atom. And what we're interested in here is not describing the motions of the atoms in the rest frame of the observer or anything like that. We're interested in the internal state of the atoms. And we know that this is described by quantum mechanics by a wave function, and that whenever we observe an atom, it's going to collapse a wave function down to be in one of the eigenstates, one of the long-lived states that we know about from the Schrödinger equation. And here's one of them. We're calling them level 1 and level 2. And so we can just write down an expression for the rate at which level 1 decays to level 2, and level 2 has to decay at the negative rate of that, if you like. And so the total number of particles are constant. dN1 by dt plus dN2 by dt equals 0. And then we have this equation here. So this equation consists of very simple things. One is the Einstein A coefficient. The B coefficient is the rate at which you go from level 2 to level 1, say, multiplied by the intensity. Is induced thing. This is Einstein's work from 1915 or so. And then we have C21, the collision rate. So this is the interaction rate between the particles in the plasma and the radiation field. So we have this simple looking equation. The problem is that this equation has a J bar in it, and that bar means it has an averaging associated with the intensity. So it's I nu averaged over frequencies and averaged over angles over the whole plasma. So you can imagine looking in the middle of that figure and seeing rays going through that point, and you have to add up all those intensities. And so what we have down at the bottom here is just the angular part. I've omitted the frequency part. I've omitted the integral over all the rays, just for notational convenience, but it should include that. So what we have is two coupled equations. One is what looks like an equation for dN by dt, and we're going to set those to 0 because what we believe is that the thing's going to reach a steady state. So we've got an oven. There's a flux of radiation coming from underneath the sun, and it's emerging out from the sun, and it's in a steady state. When we observe the sun, that's what we see in some time and spatial average. So, but the thing then is that with dN by dt equals 0, so we have equality in those two terms in equation 1. And what does this look like then? So here are the same thing. Sorry about the number of equations. And here are basically the same set of equations, just written out in some more detail. And basically in bold, you can see to get the level populations, i.e. the state of the hydrogen atom, we need the radiation field J. But to get the radiation field, we need the state of the atoms. We need the populations. So the question is, how do we go about making these two things equivalent or not equivalent, but the same? How do we make this condition that the rate of change of the atoms is 0 at the same time as solving the radiative transfer equation? And this is all that non-LTE radiative transfer is all about. That's all it is. Okay, we're going to assume something called complete redistribution. We had that discussion last week, a little airy-fairy one about partial redistribution, but let's forget that for the time being. And what that essentially means is that the bottom equation, at all frequencies across the line, J nu over alpha nu is one number. It's basically just the ratio of N2 over N1. Okay, so if I ignore the -1 on the bottom there, I get N2 over N1 times some numbers. And that's basically what you got to remember. So now what that means is we go back, we've got the numbers in one equation. And if we can solve this radiative transfer equation, we've got numbers in this part of the equation and in the tau part of the equation, because tau is just basically the number of particles in the lower level times a cross section. So we've got two equations, one explicit in n, that's the equation 1, and one implicit in the numbers, number densities. That's basically what we've got here. Now, if I play with this equation number 1 and set that to 0, I can show just with simple algebra that this corresponds to the top equation there. The source function is 1 minus a small fraction times the j, and plus a small 1 minus a small fraction times the j plus a small term times b. So what this is telling us here is that the source function, the number ratio of the two number densities here, is given by a scattering terms. Namely, there's the first term is saying, you know, I've got a certain intensity of radiation, and if I'm not collisionally destroyed with a fraction of epsilon, I just re-radiate myself. That's all it's saying. Plus epsilon b. What's this? This is the coupling between the number densities and a small number times the Planck function. So again, this just comes from playing with the number densities and defining this number epsilon as this, which in the Wien limit is very close to this. What is this thing? This is the ratio of which in an upper level of an atom, the atom population gets collisionally knocked to level 1. So that's collisional destruction of the level. So it's basically an incoming electron hits the atom, makes the atom decay to the level 1. And now we've got the ratio of that to itself plus the Einstein A coefficient. So this is the ratio of collisions to the spontaneous emission of radiation, roughly. Okay. Now, this is the number that is going to turn out to be relatively small for strong lines. Look at the case of A is greater than C, then this is just basically C over A. That's the fraction of time that the collision occurs. That's very small. If that number is very small, we look above and we see that the source of radiation in the transfer equation is going to be close to J bar, very close, actually, and only a tiny fraction from B. Now, B is a local number depending on temperature, but J doesn't depend on any local number, depends on the local numbers to the extent that the radiative transfer equation is relatively local. Okay. So we saw in the earlier talks that we can write down, given a source function, so if we write and start with a number here, and we just make a guess for J bar, we can compute this thing. We put J bar equals B, if you like, and then with that SL equals B. So then we would start with a Planck function. And now, given this Planck function, we use the boundary conditions to compute the J bar. And then we get this equation here. All I'm doing is substituting J bar with this thing. This is now the solution to the transfer equation, the formal solution. So given SL, I compute that, and I can put it back in here. This is integrals, because this is integral over space, over angle, and over frequency. This is local. So this is a non-local part, and this is the net source function. So here's the radiative transfer in operation. It's all encapsulated here for a two-level atom. Now, if I literally do this, and I just use the formal solution like I was showing you in the earlier talks. So I literally just say, well, I'm gonna take what I think my guess of SL is, and I'm going to compute the lambda operator. That's just an integral over those three variables. That's all it is. And I put it in here. This does not converge properly. And one solution then is that when I say converge, I mean you can start with a value here and compute a new value, and then you can stick it back in here and compute a new value, etc., etc. You're going to need a lot of iterations to make any progress there, basically because the answer that's given often is that the photons transport one mean free path at a time, and if your atmosphere is 10 to the 4 mean free paths of the photons long, then it's going to take many iterations. So that's not appropriate. It's not suitable. This was already known in the 50s and 60s. So let's look again at this equation, and I'm just recovering here what we just did, just to cement things. These are the actual equations we're gonna look at solving here. And S is the lambda operator on J. That's all we're going to do at the bottom. So let's look at what this looks like. So I just rearranged some terms in that equation. That's all I'm doing. And I've written SL, and now I've written FS at the top. That just means formal solution. That means I'm literally taking some kind of initial source function, and I'm iterating on that. So what I've done is I've said S equals 1 minus epsilon J plus epsilon B. And now I've taken the S terms on the left-hand side, and I've gathered the multipliers and put them in the right-hand side as that. That's just a number, right? For each depth point, that's just a number, that bracket with -1. Now, the problem is that this is costly to invert because as well as being non-convergent quickly, and maybe not even converging, but looking like it has. So what the problem there is that's then, say you have 50 depth points in your atmosphere, and you have 50 angles, and you've got, 3 angles, and you've got 50 wavelengths. That's 750 by 750 matrix, which is not a big deal for us these days on a one-dimensional. But imagine doing this in 3D. Then you've got 750 times 50 squared. It's an enormous number of size matrix, a full matrix, which you would need to basically solve the linear system in this fashion to get this to converge. And it's just totally not going to work. Instead, what we're going to do is we're going to formally write a trick. The trick is to write lambda as some approximate thing plus the real deal minus the approximate thing. So we've done nothing. On the other hand, what we can do is then look at this equation, and the equation we're looking at is the one at the top. But what we do instead is, instead of putting lambda, we put in a lambda star, and we split it up into two places, which is lambda minus lambda star, okay? And now we have a different scheme. This is equivalent to what Jacobi did 100 odd years ago, and it's called operator splitting. So we split the operator into an approximate part and an accurate part here, but we have to remove that one. And what we end up with is a scheme like this. So we start with our whatever SL is, we make our guess, and then we compute the formal solution. We're not inverting anything here. This is just lambda operating on S, so that's fast. And whatever lambda star we've got, we just subtract this off. And we've got to define what this lambda star might look like. But then we have this thing. We have the actual next update of this thing. So I start with an iterate number n, and then I write it in two terms. So we write the first term as, we don't know what Sn plus 1 is, but you can certainly see that I'm allowed to split it in this way. I moved this to the left-hand side, and then what we end up with the formal solution looking like this, we end up with an equation that looks like that, which is nothing other than this expression down here. Now, I'm sorry about all the equations, but this is the minimum I can get away with to show you what's going on here. So if I look at the difference between S and N plus 1 and S and L, I can write it as a formal solution minus the SNL. Now, SNL we know. We can compute the formal solution quickly. But now, what we've done is we multiplied it by 1 minus epsilon times a lambda star. And we better find a good value of lambda star that makes this thing go smaller and smaller as time goes on. That's the goal here. But what you can see here is that if this number is a small number, so if this number is about epsilon times lambda star times 1, so if this thing is close to epsilon, right, then we get the change in S is the change we would get if we just iterated normally divided by epsilon. So we get much, much bigger changes. So there's some hope if we can find a lambda star of doing this. So the lambda star that people use actually to do this for a 2-level atom depends on various assumptions you can make. And this is the performance that you get by iterating for a Planck function equals 1 from optical depth 10 to the minus 2 to 10 to the 4 in a spectral line. And the actual solution, the real solution is the dotted line here, so the dots on. If we just use classical iteration, so we don't accelerate the lambda operator or approximate a lambda operator at all, each graph shows 20 iterations, and we've only got this far. It looks like the source function has become the Planck function back up here, but it's actually right in here where it's essentially starting to depart significantly. And this is a range between 1 and 10 to the minus 2. So this is really going slowly, as I said. So it's not really converging. It looks like it might have converged. The changes are very small here. And you might be tempted to say, it's changes of 10 to the minus 4. That's good enough for me. No, you've got the wrong source function. Here's what we have to do. Now, what you can do is, what Sharma did was he basically looked at this operator, lambda star, and came up with some physics using Eddington-Barbier relations about non-local places. So lambda star contained places information at different depths in the atmosphere in order to build one which is as a guess of what lambda star is. So you can imagine the lambda operator being having contributions from different parts of the atmosphere, but in an efficient way where he's found using the Eddington-Barbier relation what the intensity is to make this thing go quicker. And this has become clear as I talk through this thing. So in 20 iterations, he's got the exact answer after about 2 or 3 iterations, to within what we can see on this figure. Now, the other thing you can do is to say, well, that's too difficult. I don't want to use a full non-local operator. How about we just use the local component? What does that mean physically? It means that this is just a number operating on this thing here. It doesn't have an array of numbers, a matrix of numbers operating on this, just one number. It's just local. So it only knows about what's going on locally. And just with that local part of the operator, you can see in 20 iterations, we're doing a whole lot better than we were there. And significantly, the gaps are still fairly large. So you know you haven't converged at this level here. And then there are other ways of doing this. Auer came up with a nice sort of mathematical trick to make it converge much quicker. And you can see the operation of these operators, these approximate operators, really is doing the job for us here. But remember, we have a linear equation in the corrections here. This is all linear, and this is just a matrix, which is easy to invert. That's the other thing about this one is very difficult to invert because of the vast numbers. As I said, this one is easy, especially if this is a scalar and not a matrix. Okay. So let's look at some solutions here. Now, if I look at the sun and I put in something like hydrogen or magnesium or calcium, then I look at, as a function of the line center optical depth. So what's that? That's just the number of mean free paths between the surface and the depth in the atmosphere where I'm trying to calculate this thing. And you can see that if we have a value of epsilon, so this is how strongly the radiation is coupled to the gas, to the plasma. So if this number is big, that means there's a lot of coupling, and we see this, for a Planck function that's unity, for a source function that's 1, we can see that we go down to a depth of about 10 to the minus 1, sorry, 10 to the plus 1, and the source function equals the Planck function beneath that, but it's dropped. It's dropped to about a value of 0.3 here at the surface. So what I'm saying is that the photons are in detailed balance all the way down in here, so that they're all absorbed, but now they're starting to escape. And so the source function itself is having to respond to that by saying, I'm not going to emit so much anymore. I don't have the population to do that, so I'm going to drop. And if you look at different epsilons, you find this very systematic pattern. And if you have a small number, like for magnesium, this might be 10 to the minus 4, 10 to the minus 6, somewhere in that range, then you know that your source function over most of the atmosphere, especially the bits you're looking at, is going to be way the hell out of LTE. LTE would have a source function that's 1 all the way across. Okay? But there are two characteristics I want to point out here. One is that when does the source function go to the Planck function? That's obviously a good clue as to understanding what you might have to do to get solutions to the transfer. It gives you a clue also of the range at which photons weakly coupled to the plasma by this small number have influence over the atomic levels and therefore over the spectrum that's emitted. So pretty much you can read off here, this is 10 to the 6, this is 10 to the 5, 10 to the 4. If I take the product of this number times this one, I get about 1. And that's just saying we have, when the total optical depth is 1 over epsilon, so that's about 10 to the 6 here, then the source function, and this is what we call thermalization, right? So that's like a data point that we can emphasize and put into our understanding. And so we would say that we know that this is going to thermalize roughly just by writing down those two numbers there and looking at the atmosphere, roughly where the source function is going to depart from the Planck function. But there's another place we can put it on, and that is just empirically, we can look at this and say, well, look, if I look at this number here, I find 0.3, I find 0.1. That's about epsilon, the square root of epsilon. In fact, it is the square root of epsilon. So I can now pretty much just look at this number, this one number here, and say, well, source function is going to have to join this point to this point. And if I draw a source function like this, I get a pretty good tracking of what it's doing here. For instance, that might be a good place to start with a non-LTE guess, for instance, instead of the guess being this one. I can write that down immediately looking at these numbers. Okay, there's the epsilon B, and there's the S goes to B. So let's vary now the epsilon, and we see this, and here's the line profile. So what is X? This is now shown as a function of optical depth. Now we look at wavelength, what the intensity looks like. So now I'm just using like the Eddington-Barby relation, say, well, what would this look like? Here's the line profile, and you can see that's not normalized in the same way here. Let's see, so e to the minus 1 is this point here, would put us here. So that's, yeah, that's about a third of that point there. So e to the minus 2 is here. E to the minus 3 will be down here somewhere. So this is what the profile looks like. So now we see small departure from LTE, larger, larger, larger. So as we go to larger and larger departures from LTE, we get deeper and deeper absorption lines. And that's for an isothermal atmosphere. That might apply, for instance, close to the temperature minimum region, just below the chromosphere and above the photosphere. Now I'm going to put on a chromosphere. All I've done is change the source function here. And I said, well, you know, the corona's hot. It's way hot. The chromosphere is a bit warmer than the corona in the models I've seen. So now I'm just going to say, well, I'm just going to put in some kind of function that looks like a chromosphere. And so we get the same behavior. We get the same behavior, except now this hotter source function here has decided to raise the source function. Now what we see is we see the continuum, and then we get a broadening of, we get a line here, which is then peaked and then drops down. This looks awfully familiar. This is saying that not only that, but look, the line profile in the logarithmic space looks like this, but it's equal to the intensity of the line center. So photons are escaping from much, much larger wavelengths from line center than they would ordinarily here. Okay, and then as we go to less and less coupling, it's harder and harder for the source functions trying to follow the Planck function, but it just can't. Now that's because it's thermalized too deep. So it's thermalized in the photosphere, and now this thing just has a tiny bit of emission over and above what you'd expect for an ordinary isothermal atmosphere here. So this is an example of chromospheric line formation. Even better, we've got ones that look like this. Now, what I've done here is also not only to add in a Gaussian profile, but I put in a Lorentzian profile of the kind that Vogt developed. And here is that profile. So here's one with it, that's pure Gaussian. That's got a little bit of line wing emission, this one does. And you can see qualitatively how these are changing, okay? You can't compare them one-to-one very easily because the scales are different, but you can see that qualitatively you get the same kind of results, except we get a more peaky profile now, because we've got photons down here. And you can see that photons actually are escaping slightly differently from the 10 to the minus 4, and that's because we got enhanced wing emission and enhanced wing absorption. Okay, all right. So what it means is, and this is something that Scott of the instrumentation group, Scott Sewell, said, he wanted to understand the formation at the outset of this, of the calcium lines. And finally, I've got there after all this weeks of presentations. And what I want you to do is look at this. So this is part of the solar spectrum, 30 angstrom out of 3000. So this is 1/100th of the width of this. This width here is 1/100th of the actual wavelength. So it's a pretty narrow region. And what you see here is absorption line like this, with superimposed lines of iron and junk on top of it. And this is because calcium is one of the strongest lines in the spectrum, in the sense of being very opaque. So this is sort of looking like one of these profiles, except and it doesn't, because what I've done here is I've looked at the chromosphere and a temperature of a photosphere, which is flat. But in fact, the temperature should go up. So what we should see is something that looks like this. And we get down below the thermalization depth, the source function becomes the Planck function, and the line profile will go up again. That's what's going on here. The entire chromosphere chromospheric signal is contained in this tiny little central region here, which is not surprising because that's where the line profile is most strong. The probability of absorption, the mean free path, is very small. And here are the photospheric wings, but they go out 20 angstrom. I mean, it's a huge line in the spectrum. You can see it in a low resolution spectrum of the sun. And this is how it's formed. Again, instead of what I've done here is shown, this is the line profile, which has no wiggles or anything in it. It's just a void profile. But here's the chromosphere. Here's the top of the chromosphere. So it's reversed from what I had before. Here's the peak of the source function, and here's the Planck function. And that explains this profile. So we have a nice explanation of this. Now, what have we learned from this? Well, this is actually a little bit further than I wanted to go. So let's look for the lessons from LTE versus non-LTE, okay? Generally, the coupling is weak. So epsilon's small, 10 to the minus something, okay? And if you look at strong lines, those are the abundant elements in the sun above about 7. Well, on a scale where hydrogen is 12 in a logarithmic scale. So this is 5 orders of magnitude in abundance. Difference between, say, hydrogen and sodium. Okay, helium is about 10%, carbon, nitrogen, oxygen about 1%, etc., etc. But in all these cases, I can just work out from the numbers, say, from Gene Averett's model or whatever model you like, a Moran model or something, you're going to get a number like 10 to the minus 4. And these are all opaque lines because they're abundant and they're the ionization stages in the chromosphere. There are lines of neutrals and singly ionized ions mostly. And so you can end up with a lot of non-local things. These spectra also have transitions between much, much higher levels that have, of course, lower populations. But those weaker lines at longer wavelengths have a much smaller value of A and a larger value of C. That's because there's not much overlap between the wave functions in the same way as there is in near the ground configurations of the atom, and also because the orbits of the electrons around the atom are just bigger. They go as some n to some positive power divided by the charge on the ion to some power, like 1. So what this means is that the weaker lines, LTE, can be quite close. So there is strong coupling. Now, the thing you have to remember is we're only learning from a 2-level atom here, so we can't really go all the way and say SL is B. Well, this is often very good for these weak lines, but the other part of the story is that the tau scale may be. Remember, the populations affect the source function and the optical depth. So, so even though epsilon might be quite large in the lines, epsilon can be quite small in the UV continua. And so what you end up with is, in a real atom as opposed to 2-level atom, you get non-LTE in the ionization. So we got basically the whole bottom line of this is we must explore multi-level atoms. Here's the calcium atom. Here's the K line that I showed you. Here's 8542. This is something that people will not be familiar with because this is a fully forbidden transition. This has a delta L of 2, and this has the same parity. So odd to even means that's a strong line. Odd to even means that's a strong line. That's just the nature of the wave functions with regard to reflection in a mirror. And so these are electric dipole transitions. These are going at 10 to the 8 per second, something like that. Okay. So radiative transfer in all the atoms and ions. This is just a list here of the evolution of this thing. And I'll get to the bottom here. A noticeable change occurred in the 1970s. The state of the art was represented by Auer and Mihalis, associated Mihalis, of course, at HAO, in building radiative equilibrium models as well as non-LTE. That just means we're solving the equation, the energy equation, assuming that the atmosphere is in a state where J is equal to S everywhere on average. That means it's radiatively heated, as we talked about earlier. In the mid-70s, a chap called Chris Cannon in Australia, who died quite young, unfortunately, I think in his 40s, part of the sort of solar groups that were in Australia at the time, which were very, very strong, came up with essentially what I talked about earlier, which is this scheme where you split the operator perturbation. And this, of course, has its roots in Jacobi. Then there was a development in terms of something where they recognized the physics of photon escape. Remember, I talked a little bit about that. And so this was an acknowledgement, or rather, they started to look at this in terms of whether photons, how far photons can go in a line, depending on the frequency in the line, etc. And then Sharman at 82 wrote a 12-page paper, which was his PhD thesis, wrote this physics-based lambda star operator, as I mentioned. And then that was implemented in a multi-level thing by Carlson with his thesis. And then later on, came up with a slightly different version, in fact, with a rather different way of writing the statistical equilibrium equations. And then this was put into the RH code by Uitenbroek in 1990, the Rybak and Hopper, and that's where RH comes from, their names. Again, I apologize for more of the equations, but it's really rather simple. We have, instead of just two equations, we have n equations. So we have full matrices of R and C, and this is the statistical equilibrium equation, where the R's are the same thing. So this is the same as we had before. It's just a level by level, we have this radiative transfer equation to solve. And we have the same problem, except we have to deal with all these levels. So for instance, this might be the ground state of iron. That could be the, this could be the ground state of iron. This could be the iron 2 ground state. And we'd have a rate equation for that. And this would be out of LTE. But the iron lines between, say, you know, n equals 7 and n equals 6 levels in iron might themselves, this might be close to 0 because of the enormous rate of collisions versus this one. And then collisions times n and collisions times n means LTE. And, you know, you're going to end up looking for a source function that's in LTE. The thing is, though, that those n's belong to the neutral and they get out of LTE because of the iron functions. Okay. So all we need then is some kind of, what we need in essence is from the transfer equation, which is J equals lambda S. Remember, S is an implicit function of the n's. If we can write that explicitly in function of n's in approximate form, we've got an equation here, which is a matrix equation in n's only, because we've eliminated j's from here by doing this thing here. So we can use a simple Newton-Raphson linearization scheme, but then we must know this, essentially this quantity here. What is the rate of change of, and P means of transition I to J, and Q means population. So this is a full matrix. It's got, on the denominator, it's got a vector, but it's a full matrix, and so we see the characteristics of the matrix going to be, you know, dependent upon a column being divided by one thing, whereas the rows will be more independent, and what have you. Okay. So we're eliminating J in favor of N or S, but now we have a matrix relating N to all the J's. What does that mean? It means all the line source functions to J. So it means that we've got N by N matrix, but we've got potentially an N by N SL to J conversion as well. In fact, we do, if each level has radiative transitions. Okay, that's not such a big deal. We're still dealing with linear algebra. So there are two approaches. The Arley methods using lambda star S and linearization. So now we have to do a bit of algebraic work to figure out what to do, and this is what Sharma did. Or we can just do it using a local operator versus a global one. Or we have something called preconditioning of the rate equations. This will become clear in a moment. Okay. So basically, the only new thing here is that we compute an error term. So we have some kind of guess at the solution already. Now, these are the J plus C's, and we know that we don't have a solution yet. So what we do is we compute statistical equilibrium. We find it's out of equilibrium. Oh, hell. This is EI represents for each level n, for each iteration n, it tells us we have a vector that's an error vector. This is basically saying this is out of balance. Okay. So what we do is we have a matrix equation, mx equals e. So now what we want to do is to write m in a form that we can invert it and operate on the e's that we have to try and make this thing go away. Here's the thing going away because we want to make the next iteration go to 0. Here are the errors here. And so we end up with an expression that looks like this. Now, the things we know are at each iteration we don't know delta n, that's what we're trying to find. We know that one, we know this one, we don't know that one. We don't know that one, we know that one. So basically what we want is we want an equation for delta n in terms of E. And so what we've got to do is eliminate delta P here. This is the only thing left that we don't know about. And this is essentially the form of the equation that we're looking at. And in the local or the simplest operators, we basically end up with an expression where this might be for each level n and each level j. They look like some kind of linear combination of these two things. And then you iterate to convergence. So that, I hope that's clear. That should be pretty straightforward. You have a matrix equation on the left in which you have an approximate lambda operator which corresponds to that white wording at the bottom. So you know what that is. You know what alpha and beta are for each I and j. And now it takes some work to compute that, but now you basically just invert that matrix, and it's an n by n matrix where n is the number of levels. So it's nothing like the one we talked about with lambda operators. It's much far smaller. And we just drive this to convergence. Another way to do it is to, and I apologize for the equations again that are going to show up here, but it's actually rather straightforward. And I put them in order just to be able to explain what we'll see here. This paper kind of changed things quite a bit, and there's no linearization involved. So you don't need to do the hard work of computing dp by dj, essentially, okay? That's not, sorry, dp by dn. That's what you're looking at doing. But these guys come up with another scheme. Now, they just have exactly the same, this is the same as the p's. This is the radiative rate though, only. And here's the statistical equilibrium equations. Now what these guys do, instead of using the full j's and everything like this, what they do is when they integrate over frequency and angle, they set some of these terms to 0, and then in the line core. So what they're doing is saying, well, in the line core, the radiation that's emitted immediately gets absorbed, and so I can algebraically cancel those out, and that corresponds to getting rid of the radiation term here altogether in the rate equation. So you just end up with collisions in the line core. But now, as you're evaluating this rate matrix, as you start in the core, this might have a contribution of 0, but now it starts to build up in the wings of the line where the radiation is transported. Okay, in the wings the photons fly around much further. So basically what they're saying is all the radiation seems to be absorbed sort of close to where you are locally, but not entirely. So they do allow some transfer here. The other trick they do is they basically rearrange the statistical equilibrium equations and say, well, when I'm calculating some of these terms, I can use the old populations I've got as a start, and then see how that works. So I know everything on the right-hand side of the equation. I don't need to linearize anything. I just write the new set of equations in terms of the old things with this special operator built in, and that's called preconditioning. Is the thing where you eliminate some of these terms depending on frequency, and the other one is just avoiding linearization essentially. And in both cases, this has been demonstrated to work very nicely. Here is your lambda operator, but they basically are using lambda s, but they don't do that. What they do is they operate a different operator, which is psi on the emission coefficient. So they've taken tau off the bottom here, so it's become much more linear. Okay, so with the lambda operators, you have S, which is n over the lower. Sorry, it's the source function, lambda operating source function, which knows about the mean free path. It's the number of emissions per mean free path. Here they've just said, no, I'm just going to write down the emission itself. And we're going to do this, and this is going to allow us, this is the old population here, NL, okay? And so what they do is they basically then just have a system which is, in which you've removed core photon scattering. So that means that you're taking away a lot of work that you don't have to compute anymore. You don't have to compute those INUs that are just doing nothing in the core. And then what you're doing is you're saying, well, I'm going to use the old versions of the populations, and as it's trying to converge those old populations, the changes will get smaller and smaller, and at the end of the day, we'll get the exact right answer. So that's what they do. So I'm going to finish up here by telling you, well, first of all, let's just, before I finish, this is implemented and expanded in RH in 1D, 2D, and 3D. So this is considerably more work that Han did, and including molecules and what have you, in the equations of state and all these other things. So basically what RH does is it takes a 1, 2, or 3D atmosphere, implements RH 92, and then Rabi and Harma, and then gets you a consistent solution for the photon distribution functions for the thermal structure in the atmosphere. Okay, that's what's done. And so this can, and this is for a multi-level. So you could, for instance, if you're interested in doing a 700 level ion 2 problem, nowadays you can do it. In other words, every single non-LTE effect is taken into account from ion 1 to ion 8 or something in your atomic model, and this will all be taken into account. There is care taken to make sure that the optically thin parts of the radiation field are properly computed from the populations. Sometimes those come up enough. So you can use this for the entire atmosphere of the sun. All right. So hopefully this is a heavy duty talk, this one, because there's quite a lot of numerics in it, but hopefully I've described the bare bones of it, so you don't have to actually, look at the papers yourself and grind down through all the mu news and omegas and God knows what else. So so in the next month or two, what I'd like to do is we're going to return to some of these non-LTE ideas and talk about escape probabilities, core saturation, blah, blah, blah. Okay, we've already looked at some of this. We're going to look at a little bit closer at what the approximate lambda operators are. I'm going to give you something about partial redistribution, and at the end of the day, with non-LTE, I want to be able to explain the entire solar spectrum to you. And what I mean by that is I'm going to assume that the particles are all thermalized, so the ion temperatures, the electron temperatures are the same. They're all Maxwell-Boltzmann. The neutral particles are the same, and we're going to take a look at an average model of the sun, which doesn't exist, an average 1D radiative model of the sun, which doesn't exist in reality. I mean, the sun's dynamic and it's readjusting itself. There's a part of the sun that I don't understand at all called the transition region, where the photons emitted from it don't appear to correspond to what we would naively expect they do. And so I'm going to try and, nevertheless, I'm going to try and explain the entire solar spectrum in terms of some empirical models which were designed to explain the entire spectrum. So in a way, it's tautological, but what I'm doing is digging in and explain why the calcium lines has the form it does, why H alpha has the form it does, why is Lyman alpha so bright, why is H alpha relatively weak compared with certain other lines, etc. And then in maybe two almost silly attempts at explaining the origin of polarized light, I'll describe some elements of spectropolarimetry. And if that is something that wants more attention and people would appreciate more in the future, you know, I can talk to Roberto and Rebecca and find out if I can present something which would which with their help would lead to a greater understanding of what HAO does with polarimetry. Okay, that's it. So today we had two guests, the redoubtable Ben Berkey and Daniela Lakatos, who's just said thanks.
Thanks, Bill.
Shall I stop the recording?
Sure.
Yeah.